Hey, can you guys hear me okay? Okay, so this thing is working. So yeah, my name is Max Koretskyi. I'm also known as the Wizard because I really like to dive deep into internals of frameworks, other stuff, and share my findings with the audience like yourself. So today we will be talking about what makes Angular fast. So it's kind of similar to what Miska talked about it, but more in a conceptual way. So I hope that this talk will be very valuable for you. Now, I'm the guy who started Angular in depth. How many of you know of Angular in depth? Okay. Oh, cool. Like 33.2%, I think. And I work for HGrid. Yeah. Our mission is to build the best data grid in the world, and as far as I can tell, we're doing a great job following our mission. The next slide is usually where I discuss, the slide is about me, where I discuss my writing activities, speaking activities, community engagements. And it's funny that I went online on YouTube to check comments for one of my talks. And the first comment was, it's interesting that this guy has never written a line of code, and yet he teaches us how to write code, how the code works. And I realized that although I talk a lot about my writing and speaking activities, I've never said that I worked as a software engineer. So I changed my slide, and I can assure you that I have been programming for about 6 years. I know what JavaScript is. And besides that, I run Angular in Depth publication. We get about 800K views a month, so it's pretty big. Yeah, I'm also very active on StackOverflow, Google Developer Expert, and just recently I won the National IT Award in Ukraine in education category. Okay, so let's talk about what makes Angular fast. And these are the three components that I distilled. So you need to write optimized code, the code that is optimized for the execution by virtual machine, V8, right, in Chrome usually. You need to use correct data structures. Particularly, Angular uses a very interesting kind of data structures that is known as probabilistic data structures. And you need to have a compiler, right? And as we all know, Angular does have a compiler. So let's start with the optimized code. What kind of code you can find if you explore Angular sources. Now, there is a document actually in the repository. It's called perf_nodes. I explored it so you can go and see all the stuff, all the interesting stuff that you can find in Angular code. What you can find there is, for example, they don't use recursive functions because recursive functions cannot be inlined. And Mishka talked about inlining how VM optimizes code. So they don't use this kind of functions. Sometimes they use regular for loops instead of for each method on array. They use linked lists instead of arrays for shared arrays. They don't use top-level variables because usually minifiers cannot rename them, so it results in a bigger bundle. They use bit fills, and importantly, they ensure monomorphic property access. Now, this is something what Mishka talked about, and I hope that what I will be talking about, or the perspective I will give you on monomorphism, will complement what Mishka was talking about. And so if you will be re-watching these talks on YouTube, I recommend that you first watch my talk, that I will give you a conceptual understanding of what monomorphism is, and then watch Mishka's talk, where he actually shows you how it manifests itself in the code. Okay, so monomorphic property access is very important, like Mishka said, and this is what I found in the docs. So it's about 100 times faster than megamorphic property access. But what is this monomorphic property access? It's a magical phrase. Well, actually, it's just a property access. Like this function, update node. It takes an object, and inside this function, we access the property x. So this kind of functions we write every day. Interestingly, these kind of functions are part of the code inside the framework that are executing very often. Usually, they are part of change detection cycle. And you can know that it can be executed several times per second. So, is this property access monomorphic or not? Well, it's impossible to tell by looking at this function, because whether the property access is monomorphic or polymorphic or megamorphic is determined during runtime by the VM. And I'll show you now and explain to you how it is determined. But first, we need to understand that property access in VM is pretty complicated. Right? Mishka talked a little bit about shapes and hidden classes and how VM stores objects. So if you're looking for more in-depth coverage, you can check out any of my talks on YouTube. Previous talks, I went pretty in-depth into how monomorphism works, how VM stores shapes. And this is a pretty complicated topic, actually. I had to read, I don't know, one article, I came back to it 3 times to reread it, and still couldn't figure out some parts. So luckily, I had some help. Benedict from V8 core team helped me a little bit to figure out some parts of it. So if you don't understand all of it, or some part of it, don't worry, because I was in the same boat. It's not easy, really. So what we need to take from this is that property access is pretty complicated. So as we all do, and VM maintainers, they want to somehow optimize that process. And inline caching, this is, again, Mishka talked about it, is the process of optimizing this property access. And the keyword here is cache. So instead of going each time trying to figure out where exactly the offset is stored, trying to resolve the shape that corresponds to an object, we can go through that long process just once and then cache it all, right? So let me show you an example. So here we have this function, getX, that returns just a property. Okay? So somewhere inside the virtual machine, particularly inside VM, every function is represented as the closure object. Okay, so closure getX. And every function has a cache. It's called feedback vector. This is the terminology VM uses. So you can think of it as just an array, very, very big array. And for each particular property access inside the function, so this is important, VM creates cache for every single property access. There is a cache there, and this is called inline cache. So what happens? Suppose now the function starts running. Right? Your code is being executed by VM. Virtual machine collects this information. It knows how many times your function has been executed, and it's all this information is stored in this cache. But besides that, there's something else that virtual machine stores there. So we call this function getX. We pass in an object. Now, if we call it for the first time, virtual machine needs to go through the process of trying to resolve the value. So first, it needs to find the corresponding shape. This is where all the metadata is stored, particularly offsets to the property. Once it has gone over that process, it knows the information that it can now cache, right? The first thing it can cache is the shape. So it stores the shape that corresponds to that object, basically the description, right, of that object. It can also store the offset. This is the information that indicates where exactly in memory you can find that property. Okay? So next time when we go through that process, we need to first compare the shapes, and Mishka showed that called if, right? He called that ID something. I forgot. Yeah, but hidden class ID, yeah. So it compares hidden class ID, and if it matches, then there's no need to go through that lengthy process again. Right? You can just pick the information from the cache. Okay, so we stored that, and there is also interesting thing called state. So VM determines the state of the cache. And inline cache is first and foremost is a cache with its properties. So every cache has entries, right, length, and capacity. So if there is only one entry in the cache, the state is defined as monomorphic. Okay, so this goes from here. Mono means one, morphic means of a form, in our case, shape or hidden class, right? It's a general notion. And this is where the phrase monomorphic property access comes from, right? So monomorphic property access is the access if the function has been called, it doesn't matter how many times, but as a parameter, you pass in object or many objects that share the same hidden class or the same shape, right? So it means that in the cache, there is only one entry. Okay? Now, we've seen that. So we know now about monomorphic property access, and it means that there's only one entry in the cache. So here I'm calling the same function 3 times. I'm passing objects with different values, but they all have the same shape because the set of keys is the same. Now, what happens if you pass in another object, right, with a different shape? The state transitions from the monomorphic to polymorphic. It means that there is more than one entry in the cache, right? In this cache that I showed you, in this cache on the closure, there's more than one shape, okay? So it goes to polymorphic state, and as I told you, every cache has the capacity. So in V8, this inline cache, the capacity is 4. So you can pass in and cache not more than 4 different shapes. Okay, so what's interesting here is that I didn't know that, but I was running some experiments, and it appears that if the object has the same set of keys, but different prototype, VM considers it a different shape. So I'm passing, calling the third time function here, and I'm doing object create to change the prototype. So now our cache is polymorphic. And if you continue calling the function and passing in different types of shapes, right, you will, the state of the cache will transition to megamorphic. And megamorphic state, it means that virtual machine still uses the cache, but it's the cache for all object accesses in all the application. Right? And Miska showed the problem with sharing one big cache, right, is that the new values will override old ones, right? And we saw that what happened when we called too many times, like 10,000 times, right? The time increased dramatically. Okay, so how does Angular benefit from it? I'm going to quickly go over that. We have different type of view nodes, and potentially, or if we follow the object-oriented programming principles, we would need to create a different classes for each different type of a view node, right? Because they all have different fields. But in order to ensure monomorphism, Angular creates a single class for all data structures, and just using some field, like for example, type field, to distinguish between what kind of node that is in runtime. Okay, so that is monomorphism. Now, let's talk about data structures, another interesting topic. And actually, before I started working on this talk, I didn't really know that such kind of data structures existed, because I don't have proper computer science background. I learn as I go. And, well, my hope is that I touch it a little bit here, and you all will also become interested in what kind of data structures exist, beyond regular data structures like array objects, right? So probabilistic data structures, why they are needed? Well, they are usually used as an optimization layer. They cannot be used by themselves because they have some limitations. I will present some of the limitations later. But they have very little requirement in memory, and they're very, very fast. So these are two characteristics of all probabilistic data structures. Now, Bloom filter is the data structure that Angular uses, and it also appears to be the most iconic probabilistic data structure in the world. Like, at least that's what the article I read said. So I believed it. Yeah. Right. So the Bloom filters are used in databases. That's like the hardcore usage. They used in networking, and they even used in cryptocurrencies. So the Bloom filter is designed to answer one simple question: is the element in the set or not? Right? It's just like an array. But if you have an array, to find out if there is an item in the array, you would just we need to go through one by one and doing the comparison, right? So 1 million elements. It's a long way to figure out if there's element in the set or not. So Bloom filter allows us to do it much quicker. And naturally, you can have two answers: no, right? Okay, element is not in the set, and yes. But it's tricky, because probabilistic data structures do not give you the answer yes. The answer is maybe. That's why they are called probabilistic. And you can do some tuning. You can actually define this probability of answer yes. And I think, at least from what I've looked at Angular, they ensure that it's always yes. I won't have time to cover how they do it, but it's interesting. So it's maybe and no, right? Varying probability. Now, I hope that by now you're wondering, how is it possible that you don't know for sure if the element is the set or not? Yeah, this slide, I forgot about it, right? So all probabilistic data structures, they share two common characteristics, and Bloom filters as well. They use hashing functions to encode items. So you feed them a good item, and you get a hashing function result, which is just a number. And they don't store entire items. So you cannot use probabilistic data structures as a replacement for regular data structures like array. They usually go one with one. So we take a set of 3 elements. I'm going to show you how Bloom filters work. Just a quick overview. Right? Bloom filters are just bit fields. So you run some value through the hashing function. In our case, for example, this is very, very primitive hashing function. It just takes the first value, produces the number. And what you do, you set this bit using bitwise operators. So for John is the whole value, right? We got just number 2. So we set the number 2. The second bit in the bit field. So then, if we need to know if John in the set or not, what do we need to do? We take John, we pass it through the same hashing functions, we get the same number, and what do we need to do now? Who can tell me? Nobody? Okay, we need to check if this bit is set or not, right? Because we know that in the beginning we set this bit, so now we just need to check it. And if this bit is set, then John must be in the array or in this set, right? But I told you that it's never yes, right? It's always maybe. The problem is that your hashing function can produce the same number for different values, right? The collisions are possible. So it may be that some other value produced number 2, and now the other value is there. So you always first check the Bloom filter, and then if you get the answer, maybe, now you can go and check the data structure that pairs with it. And this is exactly what Angular is doing. And it's using this technique in its dependency injection system. So we all know that in Angular, we have hierarchical injectors, right? That follow the pattern, the hierarchical pattern of components. Okay? So for each component, Angular creates an injector. And now, if we need to resolve the value, for example, the bottommost component requires a widget manager that is registered somewhere at the top. Now, in order to get that widget manager, the runtime has to go through multiple injectors until it reaches the topmost. And in each of those injectors, it needs to check if there is item in the set or not, right? If this widget manager is declared inside site analytics component, widget component, and so on. And again, if components or injectors contain a large number of services and you have quite lengthy hierarchy, it takes some time. So here we're using just regular data structures. And we learned that we can complement regular data structures with probabilistic data structures to perform that check. And this is exactly what Angular is doing. It adds a Bloom filter to each injector. And we know that if injector gives us answer no, it means that it's 100% correct. We can now go and check the other injector. And it's very fast. It's just one bitwise operator. It's extremely fast. So what Angular does, it first checks the Bloom filter. The first Bloom filter. If it gives us answer no, that's OK. We believe it's 100% correct. So we go up. Then we go and check the second Bloom filter. The answer is no. And only when we reach the bottom or upmost injector, or Bloom filter, we get the answer maybe. And we now know that, OK, maybe not there, so we'll just go and check the injector. And that's what Angular does. It checks the injector, it finds the service that is required, and then injects it down. OK, so that is probabilistic data structures, and particularly Bloom filter. And the last piece I want to talk about is Angular compiler. So Angular, as it appears, has a compiler. And why does Angular have a compiler? That is actually a valid question. Why does a framework need a compiler? And I asked this question on Twitter. What do you guys think? Why does Angular have a compiler? The most common answer was, well, to translate HTML-like syntax that the way we define templates to runtime code, right? Because browser doesn't understand interpolations, for example, directives. And that is correct answer. Here we have Angular-like template, and then we run the compiler over that, and it produces some JavaScript. This is the output of the new Ivy compiler. However, other frameworks have compilers too. For example, in React, we have JSX compiler. So is it the same? Does it perform the same role as in Angular? This was the question that I wondered and tried to discover. So this is similar template-like view definition in React. So we run JSX compiler over that, and it also produces JavaScript. Now, if you compare the output, however, you will see the real difference between JSX compiler and Angular compiler. The JSX compiler defines a view using JavaScript. There is no runtime code that is produced by the compiler. So it's a view definition, it's a particular definition of H1 element using a JavaScript object. Whereas Angular's compiler produces runtime code, and which is more important, it produces direct render instructions. These instructions, they're very fast, and they allow you to process changes in the framework in a very short amount of time. For example, in React, you would need to go through every single element and check if it changed or not. But with direct render instructions, each instruction knows to which element it corresponds. And for example, in our case, the instructions produced by Angular compiler, text binding, interpolation, they can just check this particular node. And as you can imagine, it's a lot faster than checking every single element that you have in the view definition. And this is, of course, enabled by the static nature of HTML templates in Angular, right? Because when you define them, Angular compiler has a lot of information to work with, so it can produce this kind of code, right? We use directives to signify which parts of a template are dynamic so that it needs to be checked during change detection run. Okay, so direct render instructions is the output of the Angular's compiler, and that is the biggest difference between, for example, JSX compiler in React. Svelte, for example, framework, the other framework that follows this pattern as well, also produces runtime code that is optimized for execution. But an Angular compiler is very sophisticated, and it allows the framework, or particularly what's important is that it produces the code that is run during change detection cycle very, very often, and this code must be most optimized. There's also the other benefit to having a compiler, and Angular team has talked a lot about that, and this is, of course, smaller runtime, right? Because if you have just one text binding, the compiler needs to produce only one or the single instruction to process that binding, right? As soon as you start adding more stuff to the template, for example, you start adding directives like ngStyle, it needs to produce more elaborate JavaScript. Same goes for other directives like ng4. But if you don't include them, if you don't use them in your template, you won't see these instructions or the runtime, the code that is responsible to, actually it's function bodies, because each of those instructions is just a function. So Angular doesn't include this logic for these functions into the resultant build. And that results in a smaller bundle. Okay, so this is a mountain. Why mountain? I always give these talks, these deep technical talks, and maybe one or two person in the audience sits and nods, right? The other ones, people just look at it. And I understand that this is difficult to get it. It's very difficult to produce, to try to elaborate and explain these technical details. But my hope is that you not just watch this talk today and think, okay, this is not something that I want to do or want to look at. My hope is that you will go home and rewatch my talk, Miska's talk, where he showed how exactly to track all these monomorphic property accesses and the effects that it can have. And then maybe you will buy a book about data structures and start reading about data structures that exist in programming, right? Because we, as regular JavaScript developers, we use arrays and objects. We don't need to know what is hash map, or I don't know, trees, all these other kind of data structures that, for example, server-side developers use. But my hope is that this talk will inspire you to go and buy that book, go read that article, go rewatch that talk, and by doing so, you will all become extraordinary developers. Thank you for your attention. Good luck.